we're going to be looking at electrochemistry in this set of videos. We'll be covering a different topic during class, and so this will be some independent learning, and then we'll practice with it when we get through the video. So take good notes, ask questions. If you have any, you can send me messages on Remind or save them for class time. Electrochemistry is the study of the interchange from chemical energy to electrical energy. So we're thinking mainly about batteries here, or using electrical energy to create chemical energy. So that would be like charging your battery. We have two types of cells. There are voltaic or galvanic cell. That's one type. Those are synonyms. So voltaic and galvanic. That is a type of cell that is a battery, and these generate useful electrical energy. Another type of cell is called an electrolytic cell, and this is a type of cell that requires energy, so it is thermodynamically unfavorable. So you can think voltaic or galvanic, those are favorable. Those are things that are going to have a delta G that's negative. As they run, they're giving off energy. An electrolytic cell is sort of like a dead battery. It needs some electrical current to make it run. A few other things to remember. We did oxidation and reduction earlier in the year. So remember that oxidation is a loss of electrons and a reduction is gain. In oxidation, because we lose electrons, we're going to have an increase in charge, and then in reduction, we're gaining electrons, so our charge will go down because electrons are negative. So two types of cells that we're looking at. A galvanic cell, these are thermodynamically favorable, and then an electrolytic cell requires an outside energy source. In these cells, we're talking about the movement of electrons as energy. So we're taking some chemical stored energy, some potential energy, and we're changing that into the mechanical energy of that electron movement, which of course is electricity. If you look at the picture below, we have a good comparison of these two cells. So the first one is a galvanic cell, and this one is a spontaneous reaction in which the energy is converted into electrical energy. So we have the electrons moving, and as they move, that's electricity, so they could power something like a light bulb. In that, we have an oxidation reaction in which something loses electrons, and then we have a reduction reaction in which something is gaining. And you can see something losing electrons over here on the left and something gaining them on the right-hand side. The same thing happens in an electrolytic cell. Something's losing electrons, something's gaining electrons. The only difference is this doesn't happen spontaneously. So these materials, whatever they are, they don't naturally want to lose and gain these electrons. And so we're using an outside energy source, got it plugged up here, and that energy source is going to force those electrons to move, whereas they wouldn't do that spontaneously. You can see down here at the bottom, we have a delta G value less than 0 for galvanic, but more than 0 for an electrolytic cell. A few other things to note, and we'll get more into this vocabulary, but the anode, okay, that's a term that we use in these cells. The anode is the one from which the electrons are leaving, so it's being oxidized. And then wherever the electrons are going, that's being reduced, and that's called the cathode. So the anode, the electrons are leaving and going to the cathode. In the electrolytic cell, the anode is negative. So the electrons would want to leave because negative and negative repel. But in the electrolytic, the anode is positive. So the electrons don't want to leave. However, they're being forced to go over here to the cathode, which is negative. They don't want to go there because negative and negative, those should repel. So that's why we need that outside energy source to force those to go to the other side. We're going to look at this animation to kind of help us understand what we're talking about when we say a cell. So first we're going to look at galvanic cells, and those are cells that are thermodynamically favorable. So we're looking at a galvanic cell using zinc and copper, and we have two what we call half cells. So we have zinc half cell over here and copper half cell over here. And then we have a voltmeter between them, so that's going to measure the voltage as the electrons move. And then we have this thing in the middle called the salt bridge, and we'll explain its importance as we move forward. So over here we have zinc and zinc sulfate. So if you can imagine, in this solution we have some zinc plus 2 ions. And this is going to this is the anode, so this is where oxidation is going to occur. So zinc is going to go to zinc plus 2 electrons over here on the left-hand side. Over here on the right-hand side, we have our cathode, and we have copper in the cathode. And then in the solution, we have copper sulfate. So there's going to be some copper plus 2 ions on this side. So the copper plus 2 ions are going to gain electrons to form copper. So over here we have zinc forming zinc plus 2 and copper plus 2 forming copper. The salt bridge connects these two. And the reason we need a salt bridge is to keep our charges balanced. So electrons are going to flow through this wire. And as they flow, we're going to get a buildup of negative on this cathode side as the electrons are coming in. So to counteract that, we have some positive and negative ions in the salt bridge, and the negative ones can flow over here since the electrons are leaving. That'll help balance, and then the positive ones can flow over here. You see, when we close this circuit, let's rewind and do that again. When we close this circuit, electrons are going to flow, so our voltage is about to go up when we close the circuit. And then the zinc is getting smaller because it's going to zinc plus 2. But the copper is getting larger because the copper ions are forming copper solid. Right? This is showing the exact same thing, but it's going to allow us to zoom in some. So over here on the zinc side, we have the zinc solid forming zinc plus 2. And you see the electrons are leaving, and they're going over here to copper. Let's zoom in here. So on this side, the zinc is forming zinc plus 2, and the electrons, that would give off 2 electrons, they're leaving from this metal, okay, which we call the anode, because it's being oxidized as those electrons are being given off. This zinc plus 2 is just going to go float around in the solution. Over here on the copper side, the electrons are coming in. We have some copper plus 2 in the solution. It's going to meet up with those electrons and form copper solid. So this cathode, where our reduction is taking place, is going to be getting larger. Right? Now here in the salt bridge we have 2 ions, potassium and chloride. You can have any ions in your salt bridge, but the purpose of them is to balance the charge. So you don't want something like phosphate that's going to make a precipitate. You just want some soluble ions. You can see here that these ions are flowing. We have chloride and we have potassium. And the potassium is positive, and it seems to be going to the right. And then we have some zinc coming here, also going to the right. So all of our positive things seem to be going to the right. And then we have some negative ions, our chloride. We might occasionally see a sulfate float by here. Those are going to the left. So why are the negative ones going left and the positive ones going right? Okay, let's look back here. Our electrons are flowing to the right. So if we look in the solution, we've got positive things coming in. So we're going to have a buildup of positive over here because the electrons are leaving. So to counteract that, here comes some negative stuff from the salt bridge. Okay, all about balancing the charges. Notice there's no electrons flowing through the salt bridge. They're going in the wire. As the electrons come over on this side, our positive copper is leaving the solution. So we're going to have a deficit of positive charge over here. So the salt bridge can help us by sending some more positive ions. So in this cell we have our anode, which is being oxidized and losing electrons. our cathode gaining the electrons, and then our salt bridge helping to balance the charge. These electrons moving from the anode to the cathode is producing electricity. So this is the way that a battery works on a really, really small scale. You've got a region with some metal, and then a region with another metal, and then they're connected, or you connect them when you put them in a flashlight or something like that. You're completing the circuit. And when you do that, those electrons can then flow. And usually in a battery, instead of a salt bridge, they'll kind of smash these together and they'll put like a salt porous substance. That way the salt can flow back and forth between the two in a really small space. Okay? This is basically how a battery works. A galvanic or voltaic cell. Looking back at the note sheet, we have this same reaction again, the zinc and the copper, and you see all the parts there. They're using the sodium chloride instead of potassium, but you see the sodium, the positive thing, going over here to counteract as these electrons move in. And then over here we have the negative chloride going over here to counteract the electrons leaving. Something with a negative charge, remember, is called an anion. So the anions always flow toward the anode and the cations toward the cathode. Above this chart we have some key vocabulary. So we have anode, where the oxidation occurs. We have the cathode, where the reduction occurs. An inner electrode is something that is often used if our reaction involves a gas, or if it involves two ions, like Fe+3 and Fe+2, and not iron solid, for example. So an inert electrode may be made of platinum or graphite. Either of those are non-reactive, and so they'll allow the electrons to flow through them into the solution and react instead of reacting with the metal itself. The salt bridge is used to maintain our neutrality, as we said, and it can be filled with a neutral salt or something called agar, which is also a neutral salt. But you could also just like dip something in salt water and drape it between the beakers, and that would be a salt bridge. The electron flow. This is something they like to try to trick us on. The electrons only flow through the wire, not through the salt bridge. So it's not like they're just running around here. Okay, the electrons only flow through the wire, and they always flow from anode to cathode. So if they switch this around and put the anode on the right, these electrons would go from the right to the left. They always go anode to cathode. Our voltmeter is measuring the potential of this electron movement, or how much energy we're getting out, and that's in volts. Below here you have some just like shortcuts for remembering some of these things. So oxidation at the anode, reduction at the cathode. It always moves from the anode to the cathode. The cathode is positive, so on and so forth. So those are just some things that we can remember. All right, we have a different reaction in this next example. Here we have MnO4 in our left cell and Fe+2 in our right cell, and we're reacting them by connecting them with a wire. They're missing the salt bridge, but we might need to draw that in later. They want us to just balance the equation. So we have MnO4 and Fe+2 going to Fe+3. Who is being reduced? Well, Fe+2 is going to Fe+3. That's oxidized, so that must be our anode. And then manganese, this would be manganese 7, right, if we did our oxidation numbers, going to manganese 2, so that's being reduced. So that would be our cathode. Okay. And remember, the electrons flow from the anode to the cathode. Now, these are a little bit more difficult to balance because you see we have oxygen on this side and we don't have any oxygen on this side. So in order to balance these redox reactions, we'll have to take a few steps in order to do that. And we can do those in class. But for now, make sure you can identify what is being oxidized and what is being reduced. Take a few minutes to read over the rest of this note sheet, and then we'll pick up at the top, balancing together, and then move on to page 4.